Dear students, welcome to the 6th online class of Control System Engineering. In last class, we studied about how to find transfer function for complex translational mechanical system and rotational mechanical systems. The complex translational mechanical system were just like a multi-loop or a multi-node based electrical network. As these multiple node or a multiple loop based network requires more than one equation, similarly in complex translational mechanical system, more than one equation is required to define the dynamics. Then we studied about degree of freedom. For degree of freedom, we have to find how many test point or point of motion exist in a system. A point of motion in a system will be defined as a such point which can move freely while all other points of motion are held stationary. And number of these test points or these point of motion will be equal to degree of freedom, and also will define number of equations required to define dynamics of a system. Then we studied about the rules which we will use to find transfer function of translational mechanical system. Then we studied inspection method in which we generalize equations of motion. Then we studied rotational mechanical system and the passive linear components like spring, viscous damper, and inertia, their torque to angular velocity relation, torque to angular displacement relation, and studied about their impedances. After this, we defined the rules which were quite similar to those of translational mechanical system. Dear students, by the end of this lecture, you will be able to find transfer function for linear time invariant rotational mechanical systems. Students, in this lecture, we will study about rotational mechanical system, and we will also give an introduction to system with gears, and also will study effect on mechanical impedances driven by gears. Students, now we will study inspection method to find system of equations for a system with degree of freedom equals to. From the last example studied in previous lecture, we have two equations for a system with degree of freedom equals to. If we look at the equation, all the impedances which were directly connected to the motion of theta 1 make a first part of equation, which is sum of impedances connected to the motion of theta 1 multiplied by theta 1 of s. The second part of equation includes mechanical impedances of those components which are common between theta 1 and theta 2. So in equation we will have subtracting sum of impedances between theta 1 and theta 2 multiply by theta 2 of s, and this will be equal to sum of externally applied torque at theta 1, which in this case is equal to T of s. Now coming to second equation, which belongs to second test point theta 2. All the impedances or sum of impedances connected to the motion of at theta 2 multiply by theta 2 of s, subtracting sum of impedances common between theta 1 and theta 2 multiply by theta 1 of s will be equal to sum of applied torque at theta 2. Now if we compare this with our second equation, J2, D2 and K are attached with the motion of theta 2 directly, whereas spring with coefficient K is connected between both nodes. So this will be our generic form of equation which we will use to find system of equation for inspection method. Dear students, now with the help of example, we will find out equations of motion by inspection method. In this example, we have a system which consists of one spring with coefficient K, three inertial components with coefficient J1, J2 and J3, and 3 viscous dampers with coefficient D1, D2 and D3. If you look at the arrangement, one end of D1 and D3 is tied to a fixed wall, so they can't move, where J1, J2 and J3 have 3 points which can rotate freely. So we have a system with degree of freedom equals 3. First point of rotation is represented by theta 1 of t. Second point of rotation is represented by theta 2 of t. And last point of rotation is theta 3 of t. Students, now we will study a generalized form for a system having degree of freedom equals 3. For first test point, equation will be like sum of impedances connected to the motion at theta 1 multiplied by theta 1 of s minus sum of impedances between theta 1 and theta 2 multiplied by motion of second test point, which is theta 2 of s, subtracting sum of impedances common between theta 1 and theta 3 multiplied by motion of third test point, which is theta 3 of s, and this will be equal to sum of applied torque at theta 1. Second equation will be like sum of impedances directly connected to the motion at theta 2 multiplied by motion of second test point, which is theta 2 of s, minus sum of impedances common between first test point and second test point, means theta 1 and theta 2 multiplied by motion of first test point theta 1 of s, minus sum of impedances between second test point and third test point, means theta 2 and theta 3, and this will be multiplied by motion of third test point, which is theta 3, and this will be equal to sum of applied torques at theta 2. For third equation, all the impedances or sum of impedances connected to the motion at theta 3 multiplied by motion of third test point, which is theta 3 of s, minus sum of impedances between theta 2 and theta 3 multiplied by motion of second test point, which is theta 2 of s, minus sum of impedances common between theta 1 and theta 3 multiplied by theta 1 of s, and this will be equal to sum of applied torques at theta 3. Dear students, now we will use generalized form studied in previous slide to find out equations for this system. Using generalized form, we have 3 equations for this system. If you see, there is no common component between the motion point theta 1 and third test point theta 3. So you will see a coefficient of 0 in first equation and third equation. The externally applied torque occurs at test point theta 1, so it will appear in first equation. For rest of the equations, rules are same. Dear students, now we will study transfer function for system with gears. Gears are used in rotational mechanical system and allow us to make variations between speed and torque. In some systems, we require more speed and less torque, where in some cases we require more torque and low speed. If you see the example of car, if you are driving a car in first gear, there will be more torque but a low speed. But if you are driving a car in fourth or fifth gear, your car will be moving at a high speed, but it will have a very low torque. Now we will study how to find transfer function for such systems. You may have observed or experienced a knocking sound from gears. This happens when two gears are loosely fitted, and this phenomena is known as backlash. We will study this in the section of nonlinearities. Now to find transfer function for system with gears, we'll assume that our system has no backlash. Dear students, a linearized model of a gear system is given in the figure. We will make analysis of this system and try to develop various relations for torque, angular displacement, number of teeth of a disk, and a radius of a disk. The input gear has a radius of R1. The number of teeth are represented by N1. The angular displacement covered is θ1, and externally applied torque is T1. The output gear has radius R2. Teeth are represented by N2, and the angular displacement θ2 is covered due to delivery torque T2. Now we will develop relations for these quantities for both gear 1 and gear 2. Students, now we will develop various relations for this gear system given in figure. When we apply external torque at gear 1, it will rotate in clockwise direction as gear 1 is connected with gear 2 with the help of teeth. Now if gear 1 will rotate, automatically it will rotate gear 2 or our output gear. The angular displacement will be represented by θ2 and the delivery torque will be equal to T2. But gear 2 will rotate in anti-clockwise direction. Now first point is the distance traveled along each circumference is the same. The distance traveled by first gear will be equal to distance traveled across second gear. For this, if you look at the second figure which represent arc length, it shows that arc length S is equal to radius multiplied by angle covered. Now both gear discs have same distance traveled, so S1 will be equal to S2, which implies that R1 θ1 will be equal to R2 θ2. The next point is the ratio of number of teeth along the circumference is equal to ratio of the radii of both discs. And the ratio of angular displacement of gears is inversely proportional to ratio of number of teeth. Dear students, further we will assume that gears of the system are lossless, which means energy applied to the gear 1 will be equally transferred to gear 2. The translational energy is force multiplied by displacement, where rotational energy is torque multiplied by angular displacement. and we'll obtain T1 theta 1 will equals to T2 theta 2 because gears are lossless and energy is completely transferred from input gear to gear. Combining all the relations we have studied, we conclude that ratio of torques T1 over T2 is same as ratio of radii of disk, which is R1 over R2, is equal to ratio of teeth along the circumference, which is N1 over N2, and these relations are inversely proportional to angular displacement ratio, which is theta 2 over theta 1. In figure you can see transfer function for angular displacement in lossless gear and for torque in lossless gear. Dear students, next topic is effect on mechanical impedances driven by gears. To understand this, see the figure in which a rotational system is given which is driven by gears. In this system, input torque or applied torque T1 of T is applied at input gear whose number of teeth are represented by N1. As input gears rotate, it with itself rotate output gear having number of teeth represented by N2, and the angular displacement covered is represented by theta 2 of T. Now we will study what impedance is experienced by input torque T1. For this, we will find a system without gears. Means we will shift all the impedances of the system to the input side of the system, where angular displacement is represented by theta 2 of T. Dear students, to study effect on mechanical system driven by gears, we will reflect the impedances from output part of the gears to input part of the gear. If you look at figure 1, it represents original rotational mechanical system driven by gears. For this reflection, we will start by writing an equation for output part of the system, which will be equal to J square plus ts plus k multiplied by theta 2 of s, and will be equal to torque 2 represented by T2 of s. Now torque T1 can be reflected to the output by multiplying gear ratio N2 over N1. If you see T1 over T2 is equal to N1 over N2, we rearrange it to find the value of T2. So output torque T2 in terms of T1 will be equal to ratio of N2 over N1 multiplied by T1. The system having reflected torque can be represented in L2, and its equation is also highlighted here. Students, now we will find output angular displacement theta 2 of s in terms of input angular displacement theta 1 of s. From the equation of previous slide given here, in this we will replace theta 2 of s. With the help of equation, we know that theta 2 over theta 1 is equal to the n1 over n2. Replacing this in the equation, we will get our desired equation in terms of input angular displacement theta 1 of s and input applied torque T1 of s. And this will reflect all the impedances from the output to input of the system. If you look at equation, all the impedances which belongs to output side are present at input side, but they are multiplied by the squared ratio of n1 over n2, where n1 represents number of teeth on input gear and n2 represent number of teeth on output gear. The transformed system after reflection is represented in figure. Dear students, now we will generalize the result from previous example. All the rotational mechanical impedances which are reflected through the gear trains are multiplied by a ratio which is number of teeth of gear on destination shaft divided by number of teeth of gear on source shaft whole square. If you see the figure 1 is our original system, where in figure 2 we have a transformed system. In figure 2, all the impedances from the load side or output side are transformed into input side. If you see the impedances, inertia J is present at the load side. At input side, inertial impedances is J multiplied by teeth ratio square. Similarly for damper and spring, both are multiplied by teeth ratio square. Dear students, now we will study with the help of example how to reflect the impedances. In this system, you have to find transfer function theta2 of s over t1 of s. Dear students, now we will start the solution. First step will be replace the passive elements with their impedances. Then we will define degree of freedom. For this system we have degree of freedom equals 1. As you can see in figure, both systems are connected with the help of gears. If any point on input side rotate due to torque, it will also rotate the second or output system. So this system have degree of freedom equals 1. In this problem, we have to find transfer function theta2 of s over t1 or input torque. So we will reflect the impedances J1 and D1 present on input side to the output side. For this reflection, we will multiply both impedances J1 and D1 by teeth ratio square, which is n2 over n1 whole square. Now T1 torque will be reflected by multiplying its ratio n2 over n1. This reflection of impedances and torque can be seen in the figure. Now equation of motion can be written as J equivalent s square plus D equivalent s plus K equivalent whole multiplied by theta2 of s and will be equal to input torque T1 multiplied by teeth ratio, where J equivalent or equivalent inertial impedance will be J1, which is inertia of input side multiplied by teeth ratio square, which is n2 over n1 whole square plus J2, which is inertia of output side. Similarly, D equivalent will be viscous damper present at input side multiplied by teeth ratio square plus viscous damper coefficient d2 of output side. If you see the figure of original system, we don't have any spring component at input side, so K equivalent at output will be equals to K2. Now solving this equation for our desired transfer function theta2 of s or t1 of s, we will get g of s equal n2 over n1 whole divided by j equivalent s square plus t equivalent s plus ke. And this can be represented in block diagram form where input is t1 of s and output is theta2 of s. Now if any of you have any questions, please ask.